Welcome back, class, to numerical methods. Today we're going to talk about numerical differentiation. Just as a review, previously we talked about more advanced methods for integrating functions. So particularly how we can use Romberg integration to get a more accurate version of our integral estimation, and then both Gaussian and adaptive quadrature so that we can get better answers with lower ordered functions. Today we're going to sort of take the opposite track and now talk about numerical differentiation and how we can use different ways to do differentiation on equally spaced data, and what the accuracy of those methods are. Then we'll talk about some how we can do this on unevenly spaced data. And then finally, we'll go back once again to Richardson extrapolation, but this time as we can apply it to differentiation. And then we'll talk about the sensitivity of our differentiation with respect to data error. So let's first go back and remind ourselves what the definition of a derivative is. And if you remember all the way back to your first calculus lesson, you were told that what we do is we take a change in y divided by a change in x. So in this case, we could say if that y is some function of x, we could say that it's f of x of I plus delta x minus f of xi over delta x. And then the next thing that we had to do to get that derivative was to shrink delta x to go to 0. And this is how we would get this derivative, right? So we would take these 2 points on a line, draw a line between them, and then start shrinking that line until we get a vanishing delta x. The same idea, we're going to apply the same approach here, but instead of shrinking it to 0, we're going to always keep some distance x. So all we have to do is go in and calculate some f of x plus delta over delta, and that's going to be our estimate for the derivative. What we're going to do to generate higher order accuracies is going to combine formulas of derivatives to get ever higher increasing accuracies. And we're going to do this within 3 categories. So the forward finite difference, a backwards finite difference, and a central difference formulation. So let's go through those one at a time. So let's first look at our forward finite difference. Let's take this case where we have a point here, and we're going to go forward. We're going to use the next point over to form that derivative. So we're going to draw a line between these 2 points. These are going to represent our derivative. So we could now take our second derivatives, right? So if we want to take the first derivative, we just draw this line between these 2 points. If we want to now get a second derivative, we need to know 2 points, right? I don't have enough information to do that. And we can do the forward difference sort of twice, right? So I can take the second derivative is just the first derivative of the first the derivative of the first derivative. So I can get that by taking we can take this derivative here and this derivative here. They're going to have different slopes, and then I can take the derivative of those 2 functions. So if I write this out, here I have the derivative, that first derivative of the function. Here I have maybe that, so maybe 1 and 2, and then I just need to divide it by the x between them, which is just going to be that distance again. So here we're going to represent the distance between points as h, like always. Right? So we can just take this difference of a difference. What you'll notice here in my forward finite difference is I have this x of I plus 2 point, right? So if I want to know the second derivative at this first point, I can't go backwards. And right, I'm talking about a forward finite difference, and I need 2 points. 2 extra points. So I have to go to 1 over and then that second 1 over. So this is why we have this 2 here. Okay, so this is going to give us our first order finite difference calculation shown here. I'm going to come back in a second to the second order terms. Now, the idea with the finite difference can be applied again and again. I could find the third derivative by bringing in information from this next point, fourth, fifth, sixth, etc. I'm not going to go through all of those, but we can just keep taking differences of differences to get these higher order derivative terms. If you want a full table, please refer to page 554 of your book, and it will show you all of these forward finite difference equations. Hopefully this feels a little bit reminiscent of our Newtonian interpolation where we took divided differences. Now I want to take a second and talk about our second order approximation. Just as a quick comment before we do that, I want to point out that the order of our error for that first finite difference was order h. So my error scales with the size of h. This isn't very good. Remember, our first estimate of the derivative with the trapezoidal method scaled as h squared. So the differences are going to be a little bit less accurate. So you probably want to move on and use a higher order derivative when possible. So let's look and see how we can do that. So what we're going to use is a series of Taylor expansions. If you remember from calculus, Taylor expansion says that f of x plus 1, so our next f of x, should be equal to f of x plus the derivative of that function times the space plus the second derivative of x over 2 times the distance squared. What we're going to do is rearrange that in order to isolate the derivative of interest. In this case, the first derivative. So I can truncate my Taylor series here and rearrange the function to get f prime alone. If I do this, I have f prime, so my first derivative is equal to 1 over h minus f of x plus f of x x plus 1, so the next step, minus my second derivative of x over 2. Now the issue is I don't know what that second derivative is, but we can go back and we can use our first order term, our first order estimate of the second derivative. So this is this equation here. So this is right back from that second one. This is that derivative of a derivative or finite difference of a finite difference. So I can take this definition, that first order estimate of that second derivative, and plug it in. When I do that, I get this equation. Now, all I need to do is collect terms, because we have all sorts of information that we know. We don't have anything that we don't know. I can collect terms, tidy it up a little bit. I can get an equation, a relatively simple equation for my first derivative finite difference formula to the second order. Note it looks a little bit different because here we have this x of I plus 2 term, so I need to look not just to the next point, but 2 points out. So we need to bring in a little bit more information when I'm dealing with that second order estimate. So the forward finite difference is going to work fine for all of these points. So if I go through here, it will work for here, 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 here. But if I get to that last point, I can't look forward anymore. There's nothing to the right. Instead, we need to use what's called the backwards finite difference estimate. In this case, instead of looking forward, I'm going to draw a line between these 2 points to estimate the derivative for this point. So it's going to be essentially the same idea. I'm going to take the point that I'm interested at, so this one, minus the previous point here, all over h. This is going to then give me my finite difference, but I'm just going backwards, right? So we can have a first order term just like we had last time, which is relatively simple. And then I'm not going to go through the math, but we can once again apply the ideas of that Taylor expansion to get a second order estimate for that derivative. And so we can do the same idea. We can go through and do the second derivative, the third derivative, the fourth derivative, etc. In all these cases, we're taking our point and only looking backwards. Okay? So we have all of these differences here. Okay? Once again, this is going to, if you want this table to reference, it's on page 555. Maybe I'll put this on here, page 555 in your book. You can have that first order estimate as well as the second order estimate. So what you may be thinking is, well, this is fine and dandy, but I can look forward and I can look backwards. So let's say I take the central point. I can look, we've talked about forward derivatives, we've talked about backward derivatives, and I'm going to get 2 different estimates, right? If I look at these 2 points, these 2 lines, their slopes are not the same. So we're going to end up with a different estimate depending on whether we take the forward difference or the backwards difference. So one idea would be to say, I'm going to actually take both. I'm going to take both estimates and then average them together. So maybe we can say that my better estimate of that derivative would be 1/2 the forward plus the backward. So we can average them. And this is going to be the idea behind my central finite difference formula. So just like I drew out before, we're going to say, we're going to take a middle point, we're going to use a forward finite, backwards finite difference, say going this way, FB, and a forward finite difference going forward, FF, and we'll take the average. And so we're going to hope that by taking the average, we should get a better estimate of that derivative. So this is the series of equations. So this first finite difference is the, if I'm talking about this point I take f of xi plus 1. So we're going to look here minus looking here divided by 2h. Notice that we don't reference the point xi explicitly. This is because I'm going to, when I do my finite differences, I have, the larger value minus the smaller value. And then when I do the averaging out, that term cancels out. Okay. And so just as before, we can do our Taylor expansion idea to get a second order estimate here. And then we can do the same thing for second order derivatives, third, fourth, etc., at both the first approximation and then that second order. I do want to point out, though, that our error estimate for central finite difference is better than for the forward or backwards difference. In this case, my error order estimate is of h squared. So remember, for the backwards and forwards difference, it was just of h. So we're drastically improving this because we're bringing in more information about the system. This means when I take my second order case, I am now moving from a h squared estimate to a h to the fourth estimate. So in general, we want to be able to use the central finite difference method because we have much higher accuracy. However, I can only use the central finite difference for these interior points. At the end points, I can't look backwards for the first point, and I can't look forward for that last point. So at the beginning and at the end, I always have to use either the forward for the first one or the backwards for the last one. But on the inside points, we should always use the central finite difference because we'll get a much better estimate for my derivative. So let's go and put this into practice. So let's estimate the derivative for a function using forward, backwards, and central difference formulas centered on x equals 0.5 and using a step size of 0.25 of this polynomial. In this case, the true value is negative 0.9125, and this is going to help us estimate the error. Okay, so let's get to it. So first, we're going to go through our different orders. So here I've written out the forward difference formulas. And we're going to need to pick which order that we should use. Well, the best order that we can have is this second order estimate. So we're going to go with our second order estimate because we get a much lower error. So now we're going to need, I can pull out the second order estimate for backwards difference and central formulas written here and here. So now we need to figure out what the data is that we need to calculate these systems are. So I can go through here. Let me see. I can go through here and I can plug in my xi. So this is that central point that we need, and calculate that from the function we had previously. So that's 0.925. Now, for the forward finite difference, I need 2 points farther along. So I need to go to xi plus 2. Remember, h was 0.25. So this means my x plus 1 is 0.75. And then my xi plus 2 is 1. So because I've added 0.25 twice. For my backwards derivative, I need to look backwards two spaces. So if I look backwards once, that's x equals 0.25. And if I look backwards twice, that's xi minus 2 is 0. And then for all of these cases, I can go through and calculate my f of x value. Whoops. So now I can take these information and I can plug it in. So I can now put in my derivative. So the derivative at x equals 0.5 is going to be negative, let me put this in here, negative f of xi plus 2, okay? So that's, we can plug this number in. So that's negative 0.2 plus 4 times xi plus 1. So that's this 0.63638281 minus 3 times f of x. So that's 3 times 0.925 all over h 2h, where h is of course 0.25. And I can do this all out and I get, maybe I'll put it down here, negative 0.859375. This gives me a true error of 5.82%. Excellent. So now we've done the forward estimate, we can go in and do the backwards estimate. I'm going to clean this up just a little bit so I have some space. So I'll put this 0.859 and my error estimate up here so I can go in and do that backwards difference. Okay, so in this case we have 0.5. We're going to now use this formula. We can go a little bit faster. So we do negative the function value at 2 backwards, so that's 1.2 plus, sorry, that's 3, negative 3 times 1.2. Sorry, let me clear that up. We have 3 times 1.2 minus 4 times just the previous back by 1, so this value, 1.1035, plus my current value, 0.925, all over 2 times 0.25. I can do this all out, and I get negative 0.879 for a true error of 3.7%. So we can see in this case, my backwards difference is a better estimate than my forward difference. We're not guaranteed to have that, but in this case, it appears to be true. The best thing that we can do, though, is using our central difference formula. So this should give us the best estimate of all. And so we're guaranteed to get a better estimate, in fact. So in this case, we're now going to use this central difference formula, and I'm going to need to use all of the backwards and forward spaces, but I don't need to use the function value for where I currently am. So in this case, I have negative the forward space, so 0.2 plus 8 times the f of xi function value, so that's 0.636 minus 8, looking backwards one space, so 1.103 plus looking back 2, which is 1.2, all over twice my difference. So if I go in here and do this out, I have negative 0.9125. This gives me a true error of 0. So we nailed it right on the head. So you can see that our central difference is going to give us our best possible error estimation. Just like in integration, we can use Richardson extrapolation to take 2 lower order estimates of the derivative to get a higher order estimate. So just as before, if I take 2 order h squared estimates, so this is this would either be the second order forward finite difference or second order backwards finite difference. And I cut the spacing in half, so I cut h in 2, I can estimate the derivative by 4/3 my derivative of h2 minus 1/3 the derivative of h1. This will also hold for my first order central difference formula. We can go to even higher order estimates, using Richardson extrapolation. So let's say I take 2 order h2 estimates. So this would be our second order central difference formula. Or sort of coming down here in a Romberg-like estimate, we can use this formula, which says my derivative is 16/15 dH2 minus 1/15 dH1. And then we can, keep going and adding higher and higher order estimates. So this is just looking back to Richardson extrapolation, where I'm going to take pick my method, pick one spacing value h, cut it in half, do my estimate again, and then be able to have a very good estimate of my derivative, or an improved estimate of my derivative. So let's look at an example of doing this. So we can take the same formula that we've been working with and take the derivative at x equals 0.5, and then calculate that derivative using Richardson extrapolation with h equals 0.5 and h equals 0.2. So in this case, we can go in and use my first order central difference formula. Whoops, sorry. We can use my first order central difference formula, where I can calculate my derivative at 0.5. Should be my next step. If this is using, so this is my h is 0.5. So I can plug in f of 1 minus f of 0 over 2h, right? So this is my central difference formula. So when I plug this in, I get 0.2 minus 1.2 over 1 equals negative 1.0, right? So this would be an estimate, an error of 9%. And I can do this again for d equals 0.25. In this case, I take my f of 0.75 minus f of 0.25 over twice h. When I plug this in, when I plug these values in, I get 0.636 minus 1.103, this time over 0.5, because my h has been cut in half. I do this out, I get negative 0.934 for a true error of negative 2.4%. And so now I can go in and calculate my Richardson extrapolation. So remember, I have order h squared, because that's what my central difference gives me. So I can go in and say that my Richardson extrapolation estimate is 4/3 times negative 0.934, so this error, minus 1/3, negative 1, and this will give me my final value of negative 0.9125. So we get a very good estimate for that error when I do this Richardson extrapolation. So far, we've talked about ways to get relatively accurate estimates of my derivative when I have a function, and I can go in and I can take as many points as I want and space them out to increase the accuracy. But once again, we end up having a problem when we get to experimental data. We may not have an infinitely large data set or a way to repeat that. And usually we don't have a perfect spacing of the data. So one way to deal with this is to fit a polynomial to the data that we do have, so to the unequally spaced data that we do have, and then take its derivative. Here, it's useful to use Lagrangian polynomials to fit the data. Remember, we can use Lagrangian polynomials when we have unequally spaced data, while our finite difference formulas using Newtonian interpolation relied on or worked best with more evenly spaced and nicely curated data. So when I use my Lagrangian polynomial, I can then go in and take the derivative of the Lagrangian polynomial. So when I do that, I get this formula. So I can say that my derivative is my function value at x0, x1, x2, multiplied by these formula to take into account the unevenly spaced data. So let's take an example and put this into practice. So let's say we're looking at soil temperatures for soil temperatures, and we want to know what the heat flux is between at the soil and air interface, which we can do using Fourier's law, which says my heat flux is equal to K dt dz. In this case, we want to determine what that gradient is at the soil-air interface in order to determine what the heat flux is. So we can do that by taking data points down into the soil, measuring the temperature, because if I can find out what that dt dz is, we can figure out what that heat flux is using the fact that my thermal conductivity is at roughly 0.5 watts per meter Kelvin. So here, what we need to do is we need to pull back our Lagrangian equation for my first derivative, and then we can start plugging in our associated values. So let's do that. So we are interested in finding out what my derivative is at x equals 0. So at that soil air interface. So remember, we had data that was taken at 0, so at that interface, then at 0.0125 meters and 0.035 meters. So what we need to do is we need to plug in the temperature in this case at that soil air interface, which was 13.5. Now we can plug in all of our different x's. So we had 2 times the x that I'm interested in, so 2 at 0, minus our that next data point, which was 0.0125, and then that third data point, 0.0375. Okay, and then we have all over this x0 minus x1, x0 minus x2. So that's just 0 minus 0.0125, and then 0 minus 0.0375. All right, so now we can go in, we can do the second piece. Yeah, I'll have it better. We can look at the second piece. So we can take that function value of the soil, so our temperature of the soil at 0.0125, so that was 12 degrees. Maybe I'll put a little tx1, 0. So now I can go in and I can plug in these different values of x that I'm interested in. So 2 times 0 minus x0, which was 0, minus x2, which was 0.0375, all over x1 minus x0, so 0.0125 minus 0 times x1 minus x2, so 0.0125 minus 0.0375. And then I need to do my last term, which is plus my function value at 0.0375 meters into the surface. So that was 10 degrees C times twice 0 minus 0 for that x0 minus x1, which was 0.0125 over x2, so 0.0375 minus x0, which was 0, times 0.0375 minus x1, which was 0.0125. We can plug all of this in And we will end up with the answer of negative 133.33, and then we can put in the appropriate units, K per meter. Okay, so now we can go in and we can figure out what that Q is. So with our heat flux at Z equals 0, which is negative 0.5 watts per meter Kelvin. So that was just given as our heat transfer coefficient, minus my derivative, so 133.33 K per meter. So when I multiply all of this out, we have 66.667 watts per meter squared. Right? So this shows us how we can use our Lagrangian equations with analytical derivatives of the Lagrangian equation in order to get a numerical estimate for our derivative with unequally spaced data. The last major concept that I want to talk about is partial derivatives. So we may want to take a partial derivative of f of x and y, which means we can look at the derivative in both x and in y. So here, we can say partial f of x, partial f over partial x. And we can use those same ideas with divided differences from earlier in the lecture. So we can use all those same ideas, but now we're going to take one direction at a time. In our first set of derivatives, when we say want to look at our central difference formula, say, with respect to x, I keep y constant when I calculate my values, and I look and I change just x. So I do x plus delta x and x minus delta x. I can use the same idea, but if I wanted to look in the y direction, I keep x the same, and I just change y's with these different values. Here, sorry about that typo. It should be, there should be a y there, so 2 delta y. And I can do this in say, using the central difference formula for the derivatives in the first order derivatives, and we can do the same exact idea with second derivatives. So here I need to take my derivative, if I want to say take a second derivative partial f partial x, I need to look in both the x and the y direction. This gets a little bit more complicated. So what I first do is I take my central difference formula for, I take my derivative in y at this higher value of x. So maybe if I draw out a sketch, I take my derivative, my finite difference derivative, say at this point, x plus delta x, and then I take that same derivative with respect to y along this point, so x minus delta x. So I keep those two same x values, and then within each of these cases, I'm changing y. So I'm looking at the difference here and my difference here, and then I can take that difference between the two. So that's where that second delta x comes in. So notice when I'm going through here, firstly, I keep the x's the same and I change y. So you can see that here my y's are different, and so the y goes down here. Same thing over on the right-hand term, I keep my x's the same, but this time my x's between the two are different. And my y's, once again, are going to be the added value and the subtracted value. And so I get to put these down here. Now, I can now simplify this, and I come up with this term at the bottom. You'll notice that a lot of these sort of parentheses and where you do things sort of fall out, but in the end, we have the values where we have the function value where I add x and add y is positive. I have the functions where I subtract x and subtract y is also positive. And then I have the two cases where I have, x plus delta x, x minus delta y, and x minus delta x, x plus delta y. In these two cases, they're both negative. And then we end up with these 2 delta x, delta y on the bottom. Right? So we have these, it doesn't matter which case you do at the top, it's going to come out to be the same at the bottom. And we have this formula now for partial derivatives. So let's talk about error. When we're taking our central differences, or when we're taking our differences, small errors in the data are going to be amplified, right? I'm taking what's my difference between one point and another point, and I'm usually dividing, hopefully, by a small value, right? The closer that those differences are, the more accurate my derivative, right? So all of these small errors are going to start being amplified. So if I have a relatively smooth function, not so much of a problem. But if I have these sort of small errors, I can get these wiggles. So one way around this would be to fit a function first and then take the derivative of that fit function. So if you have very oscillatory data or lots of random errors, it's probably best to fit a function and then take the derivative of that fit function. Lastly, I wanted to show you how we can use MATLAB to calculate derivatives. So the first method is using a built-in MATLAB function called diff. So diff is going to go in and it's going to take the difference between those two pieces. So here I'm going to show you with some values. So here I have a bunch of times and maybe some concentrations. I can do diff of t, and we'll go through and it will calculate the difference between each of my values in t. So notice how I go 0, 5, 15, 30, 45. It shows up as 5. Diff of t shows up as 5, 10, 15, and 15. It's showing the difference between each of these spacings. Notice, though, how I have 5 points for t and only 4 points for my diff function. That's because I only have 4 intervals on which to work. Therefore, this is sort of what's expected. So what we can do is use this diff function to take the derivative. Remember, we can take those derivatives by taking the difference in the y's over the difference in x's. So we could say diff c, so our y's, over diff t, our x's. Oops, and we need to do this element by element to get the approximate derivative on each of those pieces. The other way that we can do this is using the gradient function. So the gradient function is going to determine the derivatives of f at each of the points. The difference here between gradient and difference is gradient is going to use forward and backwards derivatives for the first point and the last point respectively. So that way we have the same number of data points as we originally had. So we can say gradient times our function values times comma our x values, and we'll get our derivatives. What you'll notice is our first point and our last point give us the same derivatives that my two difference formulas gave, right? This is what we expect, right? At the beginning and the last point, we expect to have a forward difference and a backwards difference. It's in the interior points where we get a much better estimate for those different errors. We can do this, we can further do this if we give a matrix for t, and we can then calculate our partial derivatives. Let's now look and see how we can take a partial derivative with MATLAB using the gradient function. So here I've already typed in a function. So in this case, I've made an anonymous function where f equals at x comma y minus x minus 2x squared minus 2xy minus y squared. In order to get the data, I need to create both a series of x's and a series of y's. If you remember back to the beginning of the semester, we could do this with MeshGrid. So in MeshGrid, I can put in a line of points in x that I'm interested in. Let's say maybe -2, and we'll do this in increments of 0.25 all the way to 0. And then I get a series of y's that I'm interested in, so 1, 0.25. So that's going to be my spacing all the way to 3. And when I do this, I can get all of these MeshGrid points. Now I can plug these values into my function. So maybe say z equals f of x comma y. And when I do this, I get a matrix showing all of my z's at the appropriate x and y points. Now I can take my gradient. So I can say fx, fy, or maybe say dx. So my derivative of the function with respect to x, the derivative of the function with respect to y is going to be the gradient of z, and then my spacing. So my spacing is 0.25. When I hit enter, I get out my derivative with respect to x, my partial derivative with respect to y. We can plot this up using our contour map. So maybe we can say CS, so our function is equal to a contour plot of x, y, and z. And then let's label that, so we can say C label CS. And then we're going to put a hold on it so we can add in a few things in a second. So when I hit enter, we should see this pop up. So let me just make sure that you can see this. So here's the plot that pops up. We can see here the contour lines from that plot. So and then we have these labeled points sitting on here where we can see negative. That line represents -5. This line represents -4. This line represents -3, 2, 1, 0, 1, 0, +1, right? Respectively. So we can see all of this stuff. I'm going to put this to the side for a second so that we're going to then work to display that gradient. Remember, these lines are just showing the value of z. We want to see what my derivatives are. And to do this, I'm going to use an arrow plot, which we're going to call up using Quiver. So let me make sure I spelled that right. Yes, we're good. So we put in the x and y values, and then we tell it what the derivative should be. So in this case, we want it to point in the direction of steepest descent. So I'm going to put in a negative fx and negative dx and negative dy, just so it points downwards instead of upwards. So when I hit enter, I can pull back up my contour plot. Give it a second, and we'll see that we can get these gradients, which are now pointing downward. So each of these arrows are representing both the direction of that steepest descent. So how, what's the steepest direction down, and then the size is going to represent what the magnitude is. So how steep that derivative is. Right, so hopefully this has shown you how two different ways to do derivatives in MATLAB using the diff function and then using the built-in gradient function. And then we've done this in one dimension and using partial derivatives. And then we can plot up these functional forms using these quiver sets. So in review, today we've covered how we can calculate numerical derivatives when we have evenly spaced data and unequally spaced data. Remember, the key points are we can choose between central difference, forward finite difference, backwards finite difference, and then we can choose the order. And then we could get higher orders, remember, by using those Taylor expansion ideas. We then used Richardson extrapolation to get even better estimates of our function. And then we talked about how we can have, how the value of our derivatives are highly sensitive to data error. Lastly, we took some of these ideas and we applied them in MATLAB. I hope you now have a pretty good grasp on numerical differentiation, and I'll see you in class where we'll practice, or we'll put this a little bit into practice.